Okay, physical science time. Today we're talking about, hopefully very quietly, talking about fluid dynamics, which we didn't have time for on Friday, and gas laws. Fluid dynamics and gas laws. Will you go get me my trusty balloon again? Shylin, you're nearest the door. Would you help me go get that balloon? I don't remember where someone put it. Where did someone put it?
Oh, I know where it is.
Where is it?
It's in the lab.
Yeah, very good. Thank you. Shylin, go find it, please. It's like pinkish, like coral color, like pink and orange. It should be right on one of those front tables. And bring me the little pumper upper too. Okay. So let's talk first about fluid dynamics.
Gas laws? Is that the
Gas laws, yep, and gas laws. The first thing is fluid dynamics. What does it mean for something? Yes, Hunter?
Can I see the camera spot?
Yes, thank you. In fact, that you can generally do that when she's not here. What's it mean for something to be a fluid? Let's be very careful. Well, first of all, what do you understand a fluid to be?
A fluid?
Yeah, what's a fluid?
A drink.
Okay, a drink. That's what most people think when they say that.
Anything in liquid state.
Okay, anything. That's getting closer. It's still not quite right. Will, what do you think?
Matter that is in a liquid state.
Okay, that's even more specific, but still not. Actually, that's too specific now. Okay, so we agree that fluid is something you can drink. I drank it. It's fluid. This is a fluid.
Milk.
Thank you, Shylin. The pumper upper too, which is in the closet. You know what the pumper upper looks like. You remember from your Latin classes the root word of this is the same root as. I'm trying to think of a word you might actually know. Effluent? You don't know that word. Do you? What's the word effluent?
Is that that word?
Oh, you don't know. All of these words, well, those two words, I guess all of those two words, are related to the idea that this is something that can flow. Matter that can flow. The word, I don't actually know the Latin root word. Flux, I do know it. Flux is the Latin word for to flow. And flux in Latin means, I guess to whoever still speaks Latin, it means both to flow and to change. So things that are in flux, you might have even heard that word before. If your parents' marriage is in flux, that means it's changing. Probably for the worse. There's a disease people used to get called dysentery, which you know what dysentery is from your time on the Oregon Trail. That's when someone would have horrific diarrhea, and it was called by the people who had it, usually it's called the bloody flux, because the flow coming out of their body would be bloody, and that's what flux means, is flow. So the Latin word flux, which is related to fluid, and by the way, the word effluent that I said means that something kind of flows forth. You can use it metaphorically to mean that someone has an effusive or effluent personality, means that things just pour out of them, like they just can't help but talk all the time, for instance, or share their emotions. I can hear you, Kesslin. But you can also use it to mean something that is literally flowing, like a river is effluent. Yes?
Flux is also used in the movie, I think,
Be quiet,
called
please.
Blast to the Past, where it has the flux capacitor.
Oh, yeah, the flux capacitor. Yeah, that's just a fancy word. They're just using that word to be funny. But fluid is any, let's put that word in there. A fluid is any matter that can flow. Any matter that can flow. This is the math lesson, by the way, so I hope you're taking good notes. But any matter that can flow. So what should we include in that? Usually, definitely liquids, as Gunnar and Will correctly pointed out. But what else would probably count? Now that we're being this broad.
Gas.
Gas. Does plasma count? I'm not exactly sure. And you could probably make a case for things like sand, which are loosely consolidated solids. Those do flow. You might be able to, at least, you could use a fluid model to describe the flow of sand, certainly. And so fluid dynamics, let's now talk about the word dynamics. What's it mean for something to be dynamics? This is, in case you didn't know, this is the opposite, or the, maybe opposite and antonym are too strong words, but it's the reverse of the word static. And I don't mean static, well, static electricity is based on that word too, but static, remember, from static electricity, was from the Latin word to stay. So dynamic probably means the Latin word, based on the Latin word, it might actually be no. Change, yeah, to change. So we're talking about fluid dynamics. Fluid dynamics. The way, let's put this, a system changes. And remember from our CCCs that a system is just any group of what we normally call objects that are kind of interacting together. So the way a system changes. So we're talking about the way fluids, gases and liquids, can change. Let me show you that this is a... I'll just put that in my pocket. Look, where will the gas go? It flowed. It flowed out in a nice little noise of a fart. Don't laugh at that. That's a stupid. Do not laugh at that. You guys are such freshmen. Okay. So we have several properties that we're going to talk about for fluid dynamics. Let's talk about these several things. The first one is buoyancy. You know what buoyancy is. You already know what buoyancy. You know what a buoy is. Not a buoy and not a ya boy, but you know what a buoy. That's how we pronounced it. At least when I was in Bridgeport, where we all had a little hillbilly accent, we all said buoy. I don't know how you pronounce this word, but you know what this word is, right? This came up a lot in Bridgeport because of the state lakes in Bridgeport. There are what are called buoys.
It is a buoy.
What is a? It's a buoy. That's what we all call it, a buoy.
I don't know where to go. Buoy!
Yeah, we do. We all call it a buoy. But buoyancy is the idea that something can be buoyed up.
Floated.
Buoyed up. Floated, yeah. Has to do with floating. Shh.
Floating.
We'll say it has to do with floating. It's the floating force, we could even call it. And it has to do with how much water that object displaces. Has to do with fluid displacement. I'll say fluid because it's not just water. Fluid displacement.
Floating force.
So here we have some liquid. Doesn't have to be water. It's probably water. It's red though, so it's probably blood. And here we have two blocks. You can tell by the way they are that this one. What two forces are acting on this block? Remember from forces in chapter 3 or 4? No, inertia is not a force. Remember the mic can hear you this time. Yeah, gravity is acting on both of them. Let's say even that they have the same weight. They both have the same F sub g. We'll call it F sub g1. They both have F sub g1, which is also called, as Gunnar correctly points out, weight. They both have the same weight. They both have the same force of gravity, F sub g1. Which of them has a stronger buoyant force? And how can you tell?
The one floating.
The one floating has a stronger buoyant force. And in fact, how does it compare? What sign would be between weight and buoyant force? Greater than, less than, or equal?
Equal.
Try again.
Less.
Try again.
Greater.
Greater than. Yeah, it must be greater than. Actually, I mean, we're saying it's not quite raised to the surface yet. When it's at the surface, they are balanced. There's a balance between those two forces. But as it's raising up, the buoyant force is greater. And this one, must it be greater than, less than, or equal to the weight?
Less than. Equal to.
Because they both have the
Greater
same.
than. Greater.
It is sinking. Let's say this isn't the processing. I see why if you think they're equal, you probably think that this is just kind of like suspended there, just like floating in the middle. Let's say it is actively sinking.
Heavier.
Less.
Yeah, so the buoyant force, it is heavier than it is buoyant. The buoyant force must be less than the weight.
Gotcha.
F sub b. We'll say this is F sub b2, this is F sub b1. Neither of these has a net force acting on them. What's the net, both of these have a net force acting on them. What's the net force on this one?
0.
Try again, it has a net force. What direction is it? Up. What's the net force on this one?
Down.
Down. So this one is floating and this one is sinking. If the weight is less than the buoyant force, it will float. Let's write this down. If weight is less than buoyant force, F sub b, the object will what? If weight is less than buoyant force, the object will float. If weight, what's another way that we could write weight?
Mass.
No, they're not the same thing. F sub g, yeah, the force of gravity. But we're just going to write weight here. That's why I'm just pointing that out because I wrote F sub g over here and I wrote W here. If weight is greater than the buoyant force, the object will sink. I could show you, if I had to try to remember back in the lab, a demonstration of floating and sinking. But my intuition tells me that you know what floating and sinking looks like, probably.
Doesn't it also have to do with like surface area?
It has to do with total density of the object. And so what you're getting at is that, for instance, if we had, let's say we have a 1 kilogram block of aluminum, just a chunk of aluminum, okay? Just a chunk of aluminum. Fake brings up a good point. Here's some more blood. Here's a 1 kilogram chunk of aluminum. But we also have a 1 kilogram boat. Why does the boat float and the chunk sinks? Well, there's obviously something else going on here besides just weight. Well, so what must be different about them? They have the same weight. They're both on Earth.
The buoyancy of
the buoyancy of the boat is greater. Why? Well, because it takes up more. It's not about surface area. It has a greater. It has the same
It
mass.
has less dense.
Less volume.
It's less dense because it has
More
more volume. That's the next thing. Let's talk over here. This is a reminder box. This is the freshman reminder for your little freshman brain box. Rho, remember the Greek letter rho, equals lowercase m over capital V. What does this mean? We're going to write the whole thing out again. Density is rho, mass is lowercase m, volume is capital V. So the greater the volume is, which of these two things has a greater volume? Ya boy or ya other boy? Which one has the greater volume? Let me ask the other question that you answered, Hunter. Which one has the greater mass?
kilogram.
Yes.
They have the same mass. So both of them have the same value on top here. Which one has the larger volume? Let's just call them by their actual names, block or boat. Which one's the larger volume? The boat. So it has a bigger number on the bottom. So what does that mean? Density is what for the boat compared to the block? Yeah, it's smaller. For the boat has a lower density and therefore a higher buoyancy force. What's the relationship between density and buoyant force? Inversely or directly? Let me say it again. The boat has a smaller density and a larger buoyancy force. What's the relationship between density and buoyancy?
If you're more dense, you'll sink.
Yeah, but I'm asking you the relationship. I'm looking for the word inversely or directly proportional. Buoyancy and density are, Hunter?
I don't know.
Okay, you do know if you just think about it. They're inversely proportional. Rho is inversely proportional to I ran out of room. F sub B. That's pretty messy, but you can. Rho is inversely proportional to buoyant force for a given mass. Yes.
When the water is like super salty and you float on top, why?
Yeah, exactly. So there's something else going on here. So how come you, with a relatively set buoyancy, right? You don't. Your density changes maybe as you. Well, it does change as you eat and effluence, but not to a great degree. So let's say you have a relatively set density. How come you will sink, depending on your musculature and body fat, how come you will sink in fresh water but float in salt water? There must be something else that's different here.
Is the water denser?
The water, the salt water is denser. And so what we're actually doing when we say this is we're comparing the density of the fluid to the density of the object. So let's do one other little box here. This can't be in the reminder box because it's new. Let's put it here. And we'll erase this after a little while. Let's put it here. If rho sub fluid is greater than rho sub object, does this kind of notation make sense to you? You remember this from the beginning of the year, right? Let me ask it again because people were distracted by the hand sanitizer. Does this kind of notation make sense to you? We did it in the beginning of the year, but I just want to remember. This is rho sub fluid. What does that mean? What's rho? Density of the fluid, yeah. If the density of the fluid is greater than rho sub object, the density of the object, what's going to happen? If our blood is denser than the object that's in it, what's going to happen to the object? It will float. It'll float. If the density of the fluid is greater than the density of the object, we call this floating. And if density of the object is greater than the density of the fluid, what do we call that? Sinking. Let me give you a little, I call it cheat code. This is a nice little easy cheat code. In the metric system, or the SI is what we should say, in the SI, the density of water is 1 gram per milliliter. Sorry, definition, you've gone. in the SI, the density of water, rho sub H2O, is equal to 1.0 repeating grams per milliliter at 4 degrees Celsius. That means fairly cold water, water like would come out of the tap when it's on cold, or water that might come out of your fridge, has a density of 1 with an infinite number of zeros, grams per milliliter. That's the definition of gram and milliliter. It's part of the definition of milliliter. Actually, it is the definition of milliliter. It's part of what we use for the definition of gram in the SI. But the density of water is this. It's just 1. So that means if the density of an object, is greater than 1, it will, in water.
Float. Sink.
We have heard both answers. Let's try to really think about it and then answer again. The density of water is 1. So if the density of the object is greater than 1, it will what in water?
It'll float.
Sink. It'll float. It'll be in water. It's gonna sink because it's greater than the fluid.
Yeah.
Density.
If the density of the object is greater than the density of the fluid, what's the fluid here?
Sink.
What's the density of the fluid here? I just told you. What's the density of the fluid here?
1.
1. So if the density of the object is greater than 1, it will
Sink.
in water. If the density of the object is less than 1, it will float in water. This is true in air too. If I blow up this balloon again, well, this I'm not gonna drop it because it'll let go. But if I drop this balloon, what's gonna happen to it?
It'll go away.
No.
The gas.
Pretend it's tied off. And it's just the balloon itself. What will it happen? Yeah, it'll sink. Well, slowly though, right? Because it has because there's some no. Because of the air resistance in this case. There's air all around. The air is a
Molecule. Fluid.
fluid. The air is a fluid. So this that is more dense than air. Why is this more dense than air? It has air in it. Why is it more dense than air? Because it has a balloon on it too. So this is more dense than air, so it will eventually sink. It goes slow because of air resistance. What if I fill this with helium? It'll float because the density of helium is less than the density of air. Does that make sense?
Yeah.
Do you have questions about density and this part of fluid dynamics, which is called buoyancy? Remember, this is going to be on your test. This density equation is on your test. You need to remember. This is from the beginning of the year, so we're not going to cover it in great detail, but you need to remember how to do density. Does that make sense? Does anyone have questions about density before we move on? Fate does. Let's hear it.
So
Fate.
does this pretty much explain why big aircraft carriers will float?
Yep.
Because their hull is hollow.
So even though the aircraft is actually directly on the test, even though a ship that is made of very heavy and dense steel is on the ocean, it still floats. Why? Because most of its mass is steel, obviously, but most of its volume is air. So it has a smaller density than the density of water on average. Okay, 3 more principles. Let's talk about 3 more principles here of fluid dynamics before we move on. Oh goodness, no, we're not even half done. There are 3 more fluid dynamics that we need to talk about. Archimedes Principle. Pascal's Principle. And Bernoulli's Principle. We're going to describe them very briefly. Archimedes' Principle is the idea that an object that's submerged, what's submerged mean?
Underwater.
Yeah, underwater, usually water, under a fluid, will displace that fluid. When you, with your little puny freshman body, get into the bathtub water goes up, doesn't it?
Yeah.
Doesn't it?
Yeah.
Yeah.
That's
If we
right.
all,
That's
even
why you
though
build it.
even though Evan's plunge is quite large and only 2 of you got to go, even though Evan's plunge is quite large, when all the boys all the children, boys is a gender neutral term, when all the children from Crawford High School get into the Evan's plunge, it does raise a little bit. The water raises. That's Archimedes' Principle. A submerged object. Please, we can hear everything. Oh, please stop talking. A submerged object displaces an equal volume, capital V, of fluid. So if you put, if this marker has a volume of 10 cubic centimeters, and we put it underwater, How much will the water raise?
10 centimeters.
10 cubic centimeters. Yeah, it's the same. It's the same. If we put something underwater, the water will raise that much. That's how we can measure the volume of irregular solids. Remember, we did this at the beginning of the year. Put a rock, or we had a measurement of water, 30 milliliters, say. Put a rock in it, and now it says 32 milliliters. What was the volume of the rock?
32
2. No.
cubic.
Hold on, say it again.
If we had 30 milliliters of water, put a rock in it, and now it says 32 milliliters, 2 milliliters.
Centimeters.
2 cubic centimeters, yep. So that's Archimedes' principle. The story is that Archimedes was trying to figure this out, and he couldn't figure out what was going on here, and so he took a bath to think about it, and he saw when he got in the bath overflowed, and he was so happy that he had figured it out that he jumped out of the bathtub naked and ran down the streets of Athens screaming "Eureka!" You know the word "Eureka," but that word means I found it in Greek. That's what science people, like Archimedes, nakedly says, and then he was running naked. So the story is about a naked person. Pascal's principle. Let's move on. Pascal's principle is that pressure, which we'll talk about in a second, applied on a fluid is exerted throughout the fluid. Pressure applied on a fluid is exerted throughout the fluid. Here's one. What's in here?
Drink it.
What's in here?
Water.
No, mostly.
Cleaner,
yeah. It's fluid. It's a fluid. And if I apply pressure to it, look, where am I applying pressure?
Bottom.
Yeah, the middle. Where's the fluid going to come out?
The top.
It did it.
Oh, you did it again.
I always am making a...
Mr.
If I apply a pressure on the fluid, where does the fluid go? Where does the pressure go? But I didn't squeeze on the top, Chloe.
Well, it
It goes up. Goes
Taylor,
down.
do you need to leave the room? Okay.
the liquid.
Taylor,
goes away from
do you need to leave the room?
there.
Okay. Where I applied pressure in the middle, but the pressure came out the top. Same thing with this. Where if I press this down, is the pressure actually going?
Out.
No.
Up through the tube.
No. I'm pressing down on it. Where's the pressure actually going?
Going down.
Down. But the spray comes out because it's forcing pressure down into, forcing pressurized air down into the fluid, and the fluid has nowhere to go. The fluid is incompressible. This is how hydraulics work. The fluid is incompressible, and so the fluid comes out wherever the pressure is lowest. The classic example of this is if you squeeze a tube of toothpaste in the middle, the toothpaste comes out the other end, even though you didn't touch the other end. And that only applies to fluids. If you had a tube of concrete and you squeezed it, the concrete would just compress. It would get crushed. It doesn't come out the other end. Pascal's principle. Pressure applied on a fluid is exerted throughout the fluid. My balloon again.
You're stepping on the liquid.
That's okay. It's just liquid. It's gonna be fine.
That's a kind of a weird sentence. You're stepping on it.
Look at when I squeeze that, the pressure. You can see the pressure move around. What is pressure?
Pressure is a force.
Pressure has to do with force. Pressure is this. Let's take a little aside here. This is your second bit of math, but not the last one. Pressure, capital P. This is not rho. This is capital P equals capital F over capital A. P is pressure. F is force. A is area. Pressure, well, we'll talk about that in a second, but force, what do we measure force in?
Newtons.
Newtons. Good job, Gunnar. Ramrock. What do we measure area in, generally? In the SI, what do we measure area in?
Centimeters, inches.
No. Meters squared. Square meters. So pressure is measured in newtons per square meter, which is that we abbreviate this unit a Pascal, capital P, lowercase a. This marker probably has a weight of about 1 Newton. And if you can imagine a meter, a meter by a meter, so an area maybe encapsulated by the size of this little area here, from this to this and that way again. This force, the weight of this over that area, that's a very small amount of pressure. So we usually use things like kilopascals or even megapascals when we're actually measuring pressure. You might have noticed a lot of tires on the side will have the pressure reading. It'll say max pressure 56 psi, 6 bar, and then it'll give you some. It'll say 209 kilopascal (kPa). That's another. That's the SI measure of pressure. Is in kilopascals usually. So how can we? Could you do math with this? Could you do math with this?
Yes.
Yeah. We talked about how to do this kind of math at the beginning of the year. Could you do math with this?
Yeah.
Yeah. So those will both be expected of you. That'll be on the test. Both of these will be on the test. And then there will be more math that we're not going to have time for today. But there will be more math. We'll probably have another discussion tomorrow. And then on Wednesday, we will have time to work on our little worksheets and chapter review. And then on Thursday, we'll go over those. And Friday, we'll begin the test. Do you have questions about anything that was talked about today? Let me go back over it real quick. Do you have questions about how to calculate pressure?
No.
Do you?
No.
No.
Do you have questions about any of these? Oh, we forgot Bernoulli's principle, Doug. Let me write down Bernoulli's principle real quick. Velocity of a fluid and pressure exerted are inversely, what's inversely mean? Proportional. What's inversely proportional mean? Yeah, it means as one goes up,
One goes down.
yeah, the other goes down. So velocity and pressure are inversely proportional. The faster a fluid is going, the less pressure it exerts. I'm trying to think of a better example of this. The one that's given in your book is that if you take a piece of paper and you... I've never got this to work correctly, but it's supposed to be if you blow on it, which is increasing the velocity of the air coming out of your mouth, right? There's a high velocity of air, relatively high velocity of air. No, not that, Carson.
Of course he knows how to do this.
I don't. You're supposed to be able to, as the picture, look at your book real quick, because there's a picture of a boy doing it right. On page 488, figure 16 here, if you blow over, the pressure of the fluid decreases because the velocity increases. And so the paper's supposed to lift up. This is the principle. There you go. Carson can do it. The camera can't see it, but just pretend like you saw something. You look up a YouTube video of Bernoulli's
I
principle.
did it, Mr.
But listen. Good job, Gunner. Listen. This is how an airplane wing flies. The pressure, as the plane flies, the fluid moving over the wings is lesser, and so the plane is lifted up. That's called lift. That's why wings are shaped that way. Yeah, but I just told you, it's Bernoulli's principle. It's because they're going. It's because they're going fast. That's also how a helicopter works. The helicopter blades are going fast, but just in a circle. So the faster they are going through a fluid, the less pressure is exerted on them all over, and so they're able to generate a force called lift because the pressure is lower. There's another word, viscosity. That was one of your vocab words. You should just know viscosity. Basically, viscosity is how hard it is, how much a fluid resists flow. So the harder it is for it to flow, the higher the viscosity is. Pressure. Questions about pressure. How to calculate pressure. We talked about Bernoulli's principle, Pascal's principle, and Archimedes' principle. We talked about density as a reminder, and we talked about buoyancy. Do you have questions? We still haven't gotten here. I keep titling lessons 2 things and only doing the first one. Do you have questions about fluid dynamics in general?
No.
We'll talk about gas laws tomorrow.